colloquia, mostly because I think the colloquia given by people locally tend to be quite good, and today is one such case. So our speaker is Ben Feldman, who many of you know. Ben works in the area of condensed matter physics, and he studies, he works in a very active, exciting, and rapidly growing subfield of condensed matter physics. So, and he's developed the capabilities to measure thermodynamic properties of these exciting systems that people are studying. And you know, only about a handful of people in the world have those capabilities. So he's going to tell us about that. And the title of his talk is Twisted Trilayer Graphene Under the Microscope. And it's all.
Great. So thanks for the introduction. Let me see if I can. All right. So, yeah. Again, thanks, Tree, for the introduction. I'm going to tell you about some recent measurements from my lab where we've been using a single electron transistor to look at twisted trilayer graphene. That's a case. Try turning this guy on. That's a case where you have 3 graphene layers. That's what I'll focus on today. And between each of these pairs of layers, you have some interlayer twist. And I'll go through over the course of today's talk a couple of different limiting cases of interlayer twists. One in which these 2 angles are quite similar to one another, and another in which there's a mismatch between twist angles. And hopefully I'll show you that by looking locally with this special probe, a single electron transistor, we can learn something about the nature of the electronic states, and in particular, how those electronic states are modulated by the details of the structure of these 3 graphene layers. So at heart, this is really a talk about length scales. And I have conveniently left off, intentionally left off length scale for this image here, knowing that I'm looking at graphene layers which have a honeycomb lattice, knowing that I'm looking at these twisted systems. I just suggest to you guys to think to yourself, what do you think this length scale actually is, not having told you anything about the probe that I use. And you can see over the course of this talk whether you're in the right ballpark in terms of order of magnitude. All right, great. So, oops. One more thing to fix. Oh, now we're good. So I wanted to just start with a very simple view. That is, solid state physics really doesn't consist of much more than saying, hey, take some atoms that we know and love. Of course, those atoms have electrons that live in atomic orbitals, s orbitals, p orbitals, so on and so forth. And we learn in undergrad or possibly grad school that basically all you have to do is think about how these different orbitals hybridize together, depending on the details of how the atoms are arranged, what sort of lattice you get. And just by considering what happens when you have a single electron moving through this periodic potential that's created by the lattice of atoms, you get out something like this, a band structure that tells you what's the energy, the kinetic energy of that electron as a function of its momentum. And so this is an example for silicon. Don't worry about these hieroglyphs here. The point is that 1 by 1 by 1, for all the electrons that you have in your system, you fill up these energy bands up to a certain point called the Fermi level. And in many materials, all you have to do is consider just that one electron. And if it just so happens that you cut through one of these available energy bands in the system, then you have a metal. If, on the other hand, you completely fill up a set of bands, like in silicon here, and you lie within this gap between different electronic bands, then you have an insulator or a semiconductor. And so, again, this is enough to explain a lot of the physics in various material systems, copper's a metal, silicon's an insulator. And that's tremendously powerful and important. But at least from my point of view, I'm happy to say that that's not the full picture. There are corrections. Solid state physics is, in fact, quite a bit more interesting than that. And so I want to just highlight a couple of examples of cases where this breaks down. So One case is when electron-electron interactions are very strong. That is, the Coulomb repulsion is large compared to the kinetic energy that the electrons have in this lattice. In that situation, so these are called strongly correlated materials. And for example, you can have cases where you fill up half of an energy band. And even though you would predict naively from thinking about just one electron at a time that it would be a metal, turns out it's actually an insulator. And high TC superconductors are an example of that. This is some schematic phase diagram of all the interesting phases, well, not all of the interesting phases, many interesting phases that appear in these materials. And this has been for decades a challenge to understand. There's often magnetism, there's often superconductivity, and there's often a whole lot of even weirder stuff than that. And predicting at a theoretical level what exactly is going to come out as a result of these electron-electron interactions is a very, very challenging problem. The other case that I want to highlight is when you have non-trivial topology. And so there, rather than thinking of a particular solid as either a metal or an insulator, there are cases where, in fact, it can be both at the same time. And what I mean by that is in the bulk of the material, for example, you can have insulating behavior. But nonetheless, this insulator can be distinct from just the vacuum outside the material. And then there can be edge modes of various different varieties. This is a quantum spin Hall insulator that's shown in cartoon here, where you have two edge modes which are propagating in opposite directions with opposite spins, or you can have in the quantum Hall effect chiral edge modes which go around and around. And so you have this sort of hybrid system where part of the material is insulating and part of it is conducting, or you have still these conductive modes. So I mention these cases because aspects of them will come back as I go through this talk, namely aspects where electron-electron interactions lead to various kinds of symmetry breaking, ordered phases, and also where we have examples that edge modes may appear and do interesting things. So the next thing to introduce is what I would call sort of a newer class of material systems. These are van der Waals materials. That is, they consist of individual layers, which are maybe a few atoms thick, that in the plane of these layers, there's covalent bonding, and there's very strong bonding. Between individual planes, the layers are only held together by van der Waals interactions. And so they act in some anisotropic quasi-2D way when you have all of these layers stacked up, and those sorts of systems have been, again, studied for decades. But about 20 years ago now, it was realized experimentally that you can just take Scotch tape, really brand name, magic Scotch tape. There are arguments from folks in my lab about which one is the right one to use, whether the greener is better or worse. But in any case, you can take real Scotch tape and just peel off some layer from some hunk of graphite. You do this a few more times. And when you press it onto a silicon wafer, that piece of tape, there's material deposited. So this is a picture from my PhD days, actually. It's a picture of graphene and bilayer graphene and thicker graphite. And it turns out that just with an optical microscope, you can distinguish what is a monolayer of graphene. That's typically the very thinnest thing that you see on the substrate, and what is a bilayer. So this is an example of a bilayer, and you can very easily tell them apart, even though the layers themselves are just one atom thick. Now, graphene is not the only van der Waals material. There are many such materials that have been isolated in two-dimensional form since then. And pretty much any material property that exists in three-dimensional crystals, I would posit also exists in two dimensions. So you have insulators like hexagonal boron nitride, which is just like this graphene honeycomb lattice, except instead of carbon atoms, you have boron and nitrogen alternating in honeycomb. You have semiconductors like molybdenum disulfide that are interesting in and of their own right. And you have superconductors, there are topological materials, so on and so forth, magnets. All of these have been since discovered in two dimensions, and they just vastly increase the playground that we have as solid-state physicists to make and study materials. Now, also over the past couple of decades, there have been methods that have been developed to actually pick these up, individual layers. So take something like this, pick up one of the flakes and stack it on top of another flake. They don't have to be the same material. You can mix and match. You can form heterostructures. And so fairly early on, it was this analogy was drawn that this is very much like Lego. That is, we get to play with whatever material we want. We get to make whatever design we want. And frankly, we're just having fun in the lab. That's totally true. But actually, in this talk, I want to focus on two cases in particular where this analogy breaks down. That is, Lego is not a good analogy for van der Waals materials in a couple of different ways. So one of those ways you've probably already guessed is that because there is no covalent bonding out of the plane, what you can do is not only stack these materials together, but you can also introduce a relative interlayer twist. So most of these three-dimensional, most materials are rocks. You can't twist one layer relative to the other. You're subject to whatever chemistry gives you. The bonds have to be the way they are. They're just covalent. But for van der Waals materials in general, you can pick whichever interlayer twist you want. And what this does is it allows you to effectively introduce a new length scale into the problem, which is known as the moiré length. That is, you can see there's this interference pattern, this beating between the individual carbon lattices that gives you something that's much, much larger than the carbon-carbon separation. And this, of course, also affects relevant low energy bands and so on and so forth. So what does this do? Well, let's start just by considering graphene. Again, it's just a single sheet, one atom thick of carbon atoms arranged in this honeycomb lattice. And if you look in momentum space, the low energy band structure looks like this. There are these Dirac cones that meet at Dirac nodes here, right at the Fermi level. So you've completely filled up at charge neutrality up to this point here. And the carriers in graphene behave like Dirac fermions. So what about when you stack them? Actually, there also, you have quite some degree of freedom. So let me first talk about the case where there's a large twist angle between the two layers. Then the low energy states sit at these K and K prime points at the corners of the Brillouin zone. And if there's a very large twist between layers, there's also a large twist in momentum space. And what that means is that the Dirac cones that live on the top and the bottom layers are very far separated from one another in momentum. And therefore, at least at low energy, these bands can't talk to one another, more or less due to conservation of momentum. If an electron wanted to hop from one layer to the other, it would have to get a big momentum or be at high energy. So effectively, what this does is it decouples these two layers from one another electronically, at least for low energy. On the other hand, as you go further down in twist angle, then the layers start to be able to hybridize. And so the picture you should have in mind is that there are these two Dirac cones. They're separated by some change in some difference in momentum. And now the momenta, these bands cross and they hybridize the bands from the two layers as a result of the hopping of electrons up and down. And if you just happen to match the separation, that is the twist angle, to the velocity of these Dirac cones, then what you end up getting are relatively flat electronic bands. So that's what's shown here. And the idea is this is a realization. It's called magic angle twisted bilayer graphene. At this particular angle, you have a situation where the kinetic energy is very, very small. And therefore, Coulomb repulsion between electrons dominate. And in some ways, this mimics aspects of strongly correlated materials. And indeed, if you just do this is famous picture from Pablo Herrero's group from the initial report of magic angle twisted bilayer graphene, you find that if you half fill one of these bands, you get what looks like insulating behavior at half filling, and then nearby you have superconductivity. So at face value, this initially looked sort of similar to high temperature superconductors. I think that analogy has some flaws, but nonetheless, the fact that the electrons or there are effects of strong electron-electron interactions is absolutely true. And you get quite an interesting bit of physics in this material system, which hopefully I'll come back to. So I told you there were two things about van der Waals materials that the Lego analogy didn't capture. The second thing is, and those of you who have dared to walk barefoot in a house with young kids may know this, Legos are actually very rigid. If you step on them, it hurts. These van der Waals materials are just one atom thick or a few atoms thick. You should basically think of them as though they were saran wrap. And so, again, because there's no bonding out of the plane, or at least nothing beyond van der Waals, that allows the atoms locally to shift in position, and that you'll see has some important consequences. So there are various different stackings. All these pictures that I've shown you of twisted layers on top of another one, the lattices started out rigid. But in fact, that's, as I said, not the case. And depending on what sort of stacking you have, there's different energetics associated with that local stacking configuration. And it turns out these AB and BA stackings, where carbon atoms are sitting in the middle of the hexagon of carbon atoms in the adjacent layer, is the preferred configuration. If you have carbon atoms sitting directly on top of one another, that's energetically the worst situation. And so what the system does in response, particularly at relatively low twist angles, where it doesn't have to shift very much to do this, you get large regions of AB and BA stacking that form these sort of triangles. And these AA sites shrink, and then you get boundaries between these different regions. And this also has important consequences, not just to structure, but also to electronic properties. So for example, if you apply an electric field to a bilayer graphene sample like this, then you expect to have counterpropagating edge modes that are living along the boundaries of these triangles here. There are other cases where these shifts introduce ferroelectricity that you have kind of a patchwork of polarizations that point in opposite directions. So there's some real consequences to these structural changes as well. All right, so that brings me to the overview slide for the rest of the talk. I've talked so far about what happens when you stack two layers together and twist them. In this talk, as I said at the outset, we'll be talking about trilayer graphene, which has two separate interlayer twists. So I'll talk about kind of that parameter space, the sorts of physics that one expects. I'll start out by looking at a case where both angles are identical. And so there, we use, again, the single electron transistor tip. I'll describe how that works to actually image this, what I'll call helical trilayer graphene, because the angles are rotated in the same direction. And you can see that there are modulations as a function of real space position in the signal that we measure, that is, in the electronic properties of the system. And then with whatever time is remaining, hopefully there will be a little bit, I want to talk about the opposite limit, where the two twist angles are relatively mismatched, and we can use our local probe to kind of scan as a function of position and disentangle sort of where strong correlation effects are dominant, and eventually even how that compares to transport in the exact same device. All right, good. So what I've already shown you is this. We start with three layers. We've twisted two of them. This gives rise to a moiré pattern. But now that we've added the third layer, you can twist that as well. So there's an extra degree of freedom. And just like the bottom two layers have a moiré pattern, also the top two layers have a moiré pattern. And these moiré patterns can themselves interfere to create a moiré of moiré, or what I'll call a super moiré pattern. And what I want to focus on in this talk is how does twist angle, how does the coupling between layers that depends on twist angle, how does that affect the electronic states that come about? And similarly, how does this lattice relaxation that I showed you for the very low twist case, how does that change the electronic properties? So without going into all the details, I'll just point out for this system, there are two independently tunable angles. So those are represented by these two axes here, theta 1, 2 and theta 2, 3. And it turns out when you have three layers, there's not just one magic angle condition that you have. In fact, actually over this entire set of shaded regions, which correspond to either alternating twists, that is twist with one layer and twist back for the third, or twist and twist again is the helical case on this side, you get relatively flat bands for all these ranges of angles. And you can get quite a lot of fundamentally different physics by tuning the relative twist angle. So there are some cases that look very similar to magic angle twisted bilayer graphene. There are other cases where you can get one layer decoupled from the other two. And you can even get quasi-crystalline behavior. In fact, that's the most general case where there is no rigid periodicity. But what I want to start off with is this helical case where both of the interlayer angles are approximately equal to one another. So what does this look like? Well, we start with our bottom, middle, and top layer. I'm going to do this step by step because I can on PowerPoint. I'm taking both of these interlayer angles to be identical. So I'm just calling it theta for now. And there is some associated moiré wavelength that you can see by eye here. And that moiré wavelength is the same for the bottom and middle layer as it is for the middle and top layer. It's given by the graphene lattice constant divided with the first order, at least at low end. When we stack these three layers on top of one another, though, maybe you can pick out, I'm having some trouble here, but I've labeled it. There is an even longer super moiré modulation. Again, this is effectively, you should think of it as a interference pattern between the two individual moiré patterns of the two pairs of layers. Since it's interference between two moiré patterns, then that wavelength, the super moiré wavelength, is given by the moiré wavelength divided by theta again, or the original graphene lattice constant divided by theta squared, again in the low twist angle limit. And therefore, whereas you have basically three different length scales here. You have the atomic length scale A, you have the moiré length scale, which is A over theta, that's about 10 nanometers. And you have the super moiré scale, which is A over theta squared, that can be hundreds of nanometers. So this is a picture of what you expect when you take into account the fact that the local positions of the atoms in these three layers can relax. So I want to focus just first within one of these triangles here. If you think in momentum space, there are three layers, there are three K points where the low energy states sit, and they almost perfectly line up if you have the same twist angle between the layers. And so it turns out that locally what can happen is the atoms in this trilayer system can slightly shift so that effectively what you get is the K2 point, the middle layer, the states in the middle layer shift to this midpoint between the states in the outer two layers. And what this corresponds to then is a single moiré periodicity. And so that's what's denoted by the colors here. White, purple, and orange all correspond to different stacking configurations of the carbon atoms on top of one another. So the white is the preferred ABA, that is, all the atoms are shifted as much as they can be, they're not overlapping at all, that's preferred, but you also get these purples and oranges where two adjacent layers have AA stacking, either the top two or the bottom two. And interestingly enough, this breaks inversion symmetry, so I'll come back to that. So if you just calculate what is the band structure that you expect for this uniform moiré periodicity in helical trilayer graphene within one of these triangular domains, you get something that looks like this. So what you should see is that there are some low energy electronic bands. They're relatively flat, and they're separated by fairly large energy gaps to the more dispersive bands at higher energies. But it's actually even more interesting than that. Because you've broken inversion symmetry here, and because you have the topology of the draw cones to begin with, actually within one of these triangles, if you labeled the states by the Valley degree of freedom, that is if they're sitting here or if they're sitting here, K and K prime, or you can talk about their spin or their sublattice, these low energy bands that are flat have non-zero Chern numbers. And in fact, if you look for a particular valley and sum up for all the low energy bands, what is the total Chern number of that valley, these guys don't sum to zero. So what that means is that if you park your Fermi level within this gap here, you expect some sort of topological phase with boundary modes between it. And so far, I've only focused on one of these triangles. Actually, these adjacent triangles are related by C2Z flip. That is, they're related. They have opposite inversion breaking, if you will. And so what that means is that as you go from one triangle to the adjacent triangle, then actually the Chern numbers of these different bands flip-flop from one another. So along the boundaries between these triangles, you expect to have counter-propagating modes that depend on the Valley degree of freedom, K living here or K prime living there. So far, all of this is just theoretical. The theory was, I should point out, was originally put forward by Tritep Devikul, so I believe him, he's smart. And I think he was right. I say I think he was right because certain things we've been able to confirm and other things we haven't yet gotten ironclad proof of. But everything so far at least is consistent, that I've shown you. So this is a transport measurement here, shown as a function of filling factor. That is how many electrons or holes are occupying each moiré unit cell. So this is the moiré wavelength, the 10 nanometer wavelength, as a function of applied electric field across this trilayer system for a device that has a twist angle or equal twist angles of about 1.8 degrees. It turns out this is the magic angle criterion for helical trilayer graphene. And indeed, there is a band gap here when you fully fill with 4 electrons. So that just corresponds to this big band gap here. But you can see that intermediate fillings, if you put 1, or 2, or 3, there are extra features which are appearing in this plot of RxX. And what that means is that there's some sort of symmetry breaking when these bands are partially occupied. So it's a sign of electron-electron interactions. And in fact, if you just park yourself, say, near nu equals 3 at this state here, and you measure what is the Hall resistance as a function of applied magnetic field, you see a hysteresis loop. So time reversal symmetry has been broken. That's all you can really say from this anomalous Hall signal. There are some features that are similar also even at fractional filling at certain displacement fields. But you'll notice that these resistance values are not quantized. And so if you break one of these symmetries, you might think you pick a particular band with a particular Chern number and just occupy that one. That you would expect to give you a quantized RxY. You don't see it. And it could be that Tritep was wrong, but I choose to believe that Tritep was not wrong. I choose to hope, I guess, maybe not believe, that he was right. And perhaps the reason why this transport measurement is not giving you anything quantized is just because you have all of this funky domain structure. So if you measure the resistance from here to over there, then weird things can happen when these boundary modes mix at the vertices or as a result of domain physics. But in any case, from this measurement, and also, frankly, from our measurements that I'll show you in a second, we don't yet know the answer to whether these bands are truly, you can realize quantum anomalous Hall states by occupying individual bands or not. Nonetheless, this motivated us to look locally with a local probe to try and measure within one of these large triangular domains. Remember, this is hundreds of nanometers, so we should be able to do this. And our probe of choice is a single electron transistor. So this just consists of a source and drain electrode separated by tunnel junctions from some quantum dot or metal island. And the way you should think about this, so this system shows Coulomb blockade oscillations. And the way you should think about it is, if this island is small enough, trying to shove one extra electron into it costs a lot of energy because of the mutual repulsion to all the other electrons that are already occupying this island. What that means is there's a large energy gap between the highest occupied state and the lowest unoccupied state. This is E squared over C. And if you tune the Fermi level of your leads such that you're within this gap, then at low temperature, at least, an electron can't hop from the source onto the island or from the island onto the drain, and you get no current in this situation. On the other hand, if you have some gate, you can tune the energy levels of the states in the island, and at some point you go into resonance. And so an electron can hop on and then off again sequentially, one electron at a time. And so this is why it's called a single electron transistor. And basically, by measuring what is the source drain current through the single electron transistor, you get these oscillations, which you can use to figure out with exquisite sensitivity what is the electrostatic environment that the tip is living. So the way we do this in experiment in real samples is like this. We have a quartz rod, we evaporate aluminum, we oxidize it to form the tunnel junctions, we do one more aluminum evaporation right at the apex here. That gives you about 100 nanometer or 50 nanometer, somewhere in that range, island at the very tip of this quartz rod, which we can then put next to some sample which we'd like to study to learn about its electronic properties. And the trick is, all you have to do is fix the electrochemical potential of the sample that you want to study. Then as you tune what's the carrier density with some nearby electrostatic gate, that changes the chemical potential of the system that you're studying, but the electrochemical potential is fixed. And so what that means is there is a corresponding change to the electrostatic component, and that is what's actually sensed by the tip. And in that way, we can measure what is mu of n. That is, if there's a high density of states, mu is not changing very rapidly as we add electrons. If there's an energy gap or a low density of states, there's a jump in mu. In practice, we do this AC to minimize noise. So we're measuring d mu dn, or inverse electronic compressibility. And all of this is with a spatial resolution of order 100 nanometers or so. at cryogenic temperatures below a Kelvin. So what do we measure? Well, this is a helical trilayer graphene device, which we've fabricated into a Hall bar here. And if we just park our tip at some spot over top of the sample and measure d mu dn, that gives us this red trace here. So you can see there are a few peaks here. And in particular, I want to highlight these peaks on the outside, about plus minus 5 times 10 to the 12 electrons or holes per centimeter squared. Those peaks, remember, correspond to some energy gap, some incompressible state. That's the energy gap between these flat bands and the dispersive bands. We have a scanning probe, so let's use it. The first thing to do is just to say, OK, what is this behavior as a function of spatial position? So just along this black line cut here over several microns, you can see the behavior now in color as d mu dn is very homogeneous. That is, there is one peak here on either side. We can extract from the density of that peak just using simple geometry what is the effective twist angle between each layer, and it's about 1.5 degrees or so. So this is a little bit lower than the magic angle for helical trilayer graphene of 1.8 degrees. We don't see anything in this device in intermediate filling, so at least for this particular device, interactions are not going to be relevant, but nonetheless, there's some cool physics, which I'll show you. And I want to emphasize here, there's just one yellow incompressible peak on either side. If there were multiple different twist angles, then that would give rise to doubling of these peaks. And because these angles are tend to be prone to shift over the device because of how these are made, you wouldn't expect to just get one very sharp peak. This instead is a sign that actually you're getting this local relaxation to a single uniform moiré periodicity like I was showing for those triangles at the start. OK, so that's a 1D cut. What about 2D? Again, we have a scanning probe. We might as well use it. So this is now in this white box here. And what we're doing is we're measuring right in the vicinity of this peak at nu equals 4, where the flat bands are completely filled. And again, we can extract from the density of this peak what is the effective twist angle in the device. And you can see it varies just a few hundredths of a degree over 2 by 5 microns, say. Actually, even larger than that over the whole device, it's like a tenth of a degree, which is crazy. So nothing much is happening in terms of twist angle. But on the other hand, if we just ask the question, what's the magnitude of this peak at nu equals 4, that is, how big is the gap or how incompressible is it, you can see that there is this modulation which appears in d mu dn right at nu equals 4. And the length scale, you'll notice, is quite large. So this modulation that we're observing has to do with the super moiré periodicity. This is hundreds of nanometers, say 400 or 500 nanometers between these blue dots. And what I'd like to say at a qualitative level for now is that basically we've said that there should be an energy gap within each of these H and H bar triangular domains. That should show up as green or yellow. At the boundaries, at least theoretically, you expect some edge modes. This should give rise to some increased density of states, and therefore the system should be more compressible, that is, more blue. These all meet at the AAA sites, so we associate these blue dots then with regions where there's AAA stacking in the device, and we can just overlay what is this triangular pattern over top of our data. So we can look qualitatively, what is the size of these triangles? Because theoretically, at least in the absence of strain, you can just calculate from geometry. How big should these triangles be? And what we find if we compare the experimental size to what's theoretically predicted based on this local twist angle that we measure, that actually that's encoded in color here. Red means that these triangles are larger than expected. That is, for some reason, the super moiré domains are larger than would have been naively predicted. So why is that? Well, you might wonder what happens if there are twist angle differences. That is, if the twist angle between 2 layers, the bottom 2 layers, is different from the twist angle between the top 2 layers. It turns out that that only tends to decrease the super moiré periodicity. That is, it can explain the blue, but it can't explain the red. On the other hand, the size of these super moiré domains is very, very sensitive to global strain applied to the layers. So here I'm just showing one example of biaxial uniform heterostrain applied to the middle layer and plotting the super moiré periodicity that one expects as a function of that strain on the middle layer. And you can see that in most cases, actually, again, the super moiré periodicity goes down, but there's a divergence at a particular value of the strain. And therefore, strain can actually explain this data. In fact, we're not aware of any other possible explanation for why you should get any red here. I'll point out we don't know any details about the local atomic configuration. So we have a probe, it's 100 nanometer resolution. We can't actually say this atom is here and that atom is there. We're averaging over some area. Furthermore, there are various different strain configurations that you can cook up. There's uniaxial strain on one layer, the middle layer, the bottom layer, there's biaxial strain. There's all sorts of shear strains as well that you can consider. And there are several ways to reproduce this data. So even at a qualitative level or an order of magnitude level, we don't know what is the value of strain. This is just a proof of principle that strain can do this. But what we can say is that actually it's a very narrow window of strain in general, which will give rise to enhanced super moiré periodicity to red here. Generically, otherwise, it usually would tend to decrease the super moiré period. So then disaster struck, or maybe not. So we crashed our tip. And that was the end of that single electron transistor tip. These guys are very sensitive. Never crash one if you can avoid it. We had to take the sample out. We had to put in a new tip. We had to put the sample back in. There were some other dings and things that happened in the process. Actually, there were 3 thermal cycles. But eventually, we got back there. And it turned out that this was a good thing because we remeasured right in the vicinity of that same area that we had measured previously. And so that's what's shown in this lower row here. It's a measurement taken in this black box, so mostly overlapping with the bottom of the original image. And what you can see, all of these are same length scales, same color scales. What you can see is the twist angle actually has not changed almost at all as a result of what happened to the sample. That is, it looks like orange and purple are very different, but actually it's a few hundredths of a degree. So locally, the structure is actually quite similar to what it was previously. But if you measure what is the behavior in this gap between the fully filled bands, you find that now the pattern has changed considerably. So it's quite a bit more isotropic, and the spacing between these dark spots is quite a bit larger. That's, again, encoded on the same color scale here by all of these triangles now are quite red. So there are a couple of interesting things I want to highlight here. Number one, locally, the properties didn't change. Also, if you measure electronic properties, they look virtually identical. So the moiré periodicity hasn't changed as a result of this. That length scale is the same as it always was. But the super moiré periodicity now is different. And so what this means is that there's a decoupling between the 2 different length scales. That is, you can independently tune the size, the shape of the super moiré periodicity in principle with strain. Of course, we didn't do this in a controlled fashion, but one could hope to design an experiment that actually does that. And eventually, that means that you can play games. You can maintain whatever the moiré period is doing in terms of electronic properties, whether they're topological, whether you get strong Coulomb interactions. You can maintain that while changing the shape of super moiré, that is changing the shape of this network, if you believe Tritep, which again, I think you should, of topological boundary modes that exist on the surface, on the boundaries of these domains. I'll point out, again, this, it's only a select values, a small subset of the possible strain values, which will give you this enhancement. So I think fundamentally what's happening here is that energetics is helping us. That is, there is a certain preferred stacking, and there's a competition effectively in terms of how big you want these domains to be. It's a typical stat-mech problem. There's some costs associated with these linear boundaries. That is, that's where you have the stacking faults, where the local stacking changes. But as long as the stacking within domains is energetically preferred, then growing these domains actually helps you energetically overall. And so my guess is the reason why we went to this more isotropic, larger configuration is really that the system prefers to have that as its lowest energy configuration. OK, so far what I've talked about is just the behavior of the domains, the size of the domains themselves. But I've told you these stories that there should be some edge modes which exist along the boundaries of the domains. You can ask the question, can we actually address this or not? And the answer is sort of. And everything that I've shown you before, you should think of in this sort of AC measurement. That is, we apply some voltage at some frequency to the backgate. that leads to an electric field between the sample and the gate. If the sample is incompressible, the electric field penetrates through, it comes to our tip, we measure some signal. If the sample is compressible, you have a parallel plate capacitor, you're done, the tip sees nothing. But it turns out there's another option, and that option is if the sample is too resistive, that is, if the RC time constant of the sample is so long that charge can't get from the side where the contacts are to location under the tip, then charge can't come on to screen this electric field that you're applying, and you measure more in the tip than you would naturally do in equilibrium. And so we have simultaneously effectively a DC measurement of the same quantity. So what we're doing is we're parking our tip right here at some value of the current. We change our gate voltage, that changes our chemical potential. It moves us along this gate voltage axis, that is, it moves us along this curve, and then we just feed back to come back to this highest sensitivity point. And this is done on kind of a 1-second time scale. So it's effectively really DC. Even the AC is effectively DC to, as some of you call it, that is a few hundreds of hertz. But nonetheless, that measures mu directly, basically. How much do we have to adjust the voltage that we apply to the sample to come back to the same working point of our tip? And so we have d mu dn, which we can integrate to get mu of n from AC. We have mu of n, which we can take a derivative of from DC to get d mu dn. And if everything works well, these two should agree. But if the sample is too resistive, the RC time constant is too high, then you get a larger signal from this AC measurement than you do from DC. And indeed, that's what we observe. And in our sample, there's some difference. I'll call this AC enhancement. And you should really believe this DC number and not this spurious AC value. So again, there are supposed to be these boundary modes along the domains. And so if you just ask for a particular shift associated with these boundaries here, you get this band structure here. And we can do, well, we can say that in theory land, at least, you have these counterpropagating modes, which are valley polarized for one domain. They go in the opposite direction for the other domain. And we can ask the question, do we actually see this in terms of these guys should have enhanced conductance relative to the domains themselves? So the data look like this. This is an AC measurement like the ones I've been showing you so far. This is the DC measurement, noisier because it's DC, 1/f noise kills you, sorry. That's why I don't usually show it. Qualitatively, there are some similarities. That is, you see blue dots here, you see blue dots here. That aspect of it, that there's a difference in compressibility depending on spatial location, hasn't changed. But if you just take a line cut along some high symmetry axis, what you find is that the AC signal relative to the DC one, which is the one you should trust, is different. That is, it's much higher within the domains where you expect a true gap and true insulating behavior than it is, for example, at the domain walls or at these AAA sites where all of these things meet. So what this effectively is a qualitative measure of local resistance, that as we scan our tip about, when the red is high relative to the blue or higher relative to the blue, that means we are more resistive, as you'd expect within the domains. At the domain walls, at these AAA sites where they meet, the resistance is lower. We can't tell you anything quantitative from this. So I can't tell you that these are topological modes. I can't even tell you that there's no energy gap there. It could be a smaller energy gap if these guys backscatter into one another. But nonetheless, this is telling us something about the local conductivity that at least we can say with certainty the domain walls have enhanced conductivity relative to the domains themselves. And it'd be wonderful if we could actually measure locally, say, with a scan and tunneling microscope tip. Somebody should do this. And maybe I'll do it if nobody does it before me. Anyway, so I am mostly out of time. So let me summarize here, and I'll give a 5-minute Cliff Notes version of the second half of my talk. I kind of expected this to happen. So what we've done here is we've taken this helical trilayer graphene sample, and we have measured as a function of spatial position. You can see that there are electronic modulations on this hundreds of nanometer super moiré scale. We can change effectively what is the super moiré size without changing the local moiré behavior, without changing the local structure, electronic properties, so on and so forth. And we've said so far there's enhanced conductivity at the domain walls. Whether that means they're topological, we'll have to wait for another colloquium. I think there's a lot of exciting things to do One thing we're trying to do right now, of course, is go to the magic angle where interactions are strongest. Then if you really polarize into a particular band, you should see quantum anomalous Hall states very crisply in terms of their magnetic field dependence. It'd be fun to control the strain on purpose so that you can change the geometry of this super moiré pattern. And so again, there's a lot of fun stuff that one can do. All right, so in 5 minutes, let me just outline the second half of this work. It's kind of, in some sense, decoupled in that the physics is very different that I'll be describing. The link is really that we have, again, this twisted trilayer graphene system. Here now, we're looking locally with our tip at a device that has mismatched twist angles. So let me just
Ben, do you mind taking a question?
Yeah, sure.
Just out of ignorance. If you go back, yeah, the next slide would be perfect.
This one.
So you were in the chiral regime of the shaded picture, right?
Yes, we are sitting right here.
I was curious if you had looked at the other side, whether you see in your discussion of domain wall conductivity or these sorts of things, any symmetry or asymmetry between.
So these are not equivalent to one another. So you don't necessarily, so the super moiré periodicity, the fact that you have two moiré patterns which may interfere to give super moiré physics is robust. What you get in terms of relaxation may be different. It depends on details of twist angles on both sides, quite frankly. So again, Tritep and Julian have done some, and Charles here have done some very careful calculations of that. There is physics that actually Amir Yacobi has done looking at the mirror symmetric case. That's this dot right here on the opposite side, where they see effects of super moiré physics in terms of extra correlated states that are appearing with some offset. So you put individual electrons within this larger super moiré periodicity, and that gives rise to changes in electronic properties there also. So,
but in principle, this chiral edge state should not generically be living over there.
It doesn't, no, that's right. So the chirality, the thing that gives you this chiral, well, helical, I guess I would say, edge state is that you have the C2Z symmetry breaking locally within these domains, which gives you the churn bands effectively of these low energy bands. So that's what you really need to get the non-trivial topology, or at least that's an essential ingredient. Yeah. Other questions while we're doing it? Okay. So I don't want to say much. I think I'll again just give you the Cliff Notes version of this. You're safe because I have to pick up my kids not too long after this. My wife is out of town, so I definitely won't go super late. I just want to highlight, this is something that I've glossed over because I could gloss over it because the previous device was so beautiful and homogeneous in terms of twist angle. But actually, when you're assembling these layers with one another, really, we're picking them up with polymer, some squishy polymer, and we're picking up, remember, these are like saran wrap. So you pick them up, push them down against each other, and this introduces generally uncontrolled strains, generally twist angle variations, and pretty much every single sample that you fabricate is going to be a little bit different from another. And that makes it very hard oftentimes to figure out what is the intrinsic physics, what's really controlling at a microscopic level, what's going on. Okay, so here's magic angle twisted bilayer graphene, this picture that I showed you before. I said there's a correlated insulator at half filling. Actually, if you measure in the way that we did previously with a single electron transistor, you don't find a correlated insulator at half filling. So you should get a peak here, right at nu equals 2, if this thing were truly thermodynamically gapped. And oftentimes it's not. So sometimes you see that, but oftentimes you don't. And instead you get this sort of characteristic sawtooth pattern, which may have to do with sloshing of charge around in terms of different bands or different sets of portions of the bands. That's still somewhat in question, but I would put an asterisk here that just seeing a resistance peak is not enough to say that it's an insulator. And again, every sample is a little bit different. There are other cases where you have quantum anomalous Hall effect from H-band alignment, so there's quite a bit of variability here. There was this question on mirror symmetric trilayers. There also you get superconductors, you get yellow correlated insulators, you get a sawtooth. So there are certain features which repeat, and these features in general, I would say, are signs of flat band strong correlation effects. But again, every sample is a little bit different. So what we'd like to do is try and disentangle from our local probes and from other measurements, what is it really, can you look locally to figure out what's happening in this particular spot and what does it look like in terms of the physics that comes out. I'm going to skip over this one, which is the twist decoupled case, and just go here, which has 3 layers which are quasi-coupled. I'm going to skip through this guy. So we have a trilayer that has about 1 to 1.4 degrees between one set of layers and 3 to 3.5 degrees between another. And if we just measure electronic compressibility, this is the superlattice gap associated with a smaller twist angle. And it varies as a function of position. That corresponds to a variation in the smaller twist angle. The larger one we have only estimates for, but this is at least the right approximate value. And what you see is that there are these kind of dark blue, light green, dark blue, light green oscillations. This is the sawtooth in inverse compressibility that folks have seen. There's this sharp feature here, which is a truly gapped thermodynamic insulator at half filling. You can see it follows the slope of this full filling nu equals 4 line. And you can see there's some electron hole asymmetry. That is, the electrons have some particular quote unquote magic angle where these features are strongest. The holes in this exact same device obviously have a different magic angle criteria. So we see all of these effects. We can characterize what is the dependence on this smaller twist angle. And again, as I said, there's a difference in where, say, the gap for the correlated insulator is strongest for electrons and holes. There's a difference in where the sawtooth is strongest. That's just taking a standard deviation to get a strength of sawtooth between nu equals 0.5 and 3.5 here. And so this is a local characterization that we've done. We can measure thermodynamic properties, but we can't easily measure superconductivity. It doesn't show up in these single electron transistor measurements. So instead, what we ultimately did, this was in collaboration with Aaron Sharp and David Kohlhaber-Gordon's group, is we took this guy out. It was pre-characterized. We knew all of the relevant angles, and we knew, therefore, where we could pattern a transport device, a Hall bar device, and put on an extra top gate so that we could then address the aspect of superconductivity to go along with the thermodynamic signatures to try and find a link between them. And lo and behold, you put this guy in a properly filtered dill fridge like Aaron has, or David has, and you see superconductivity in black here. This is now Rxx as a function of carrier density and applied displacement field because we've added this extra top gate there. And now we patterned our device so that you can look as a function of twist angle between different contact pairs to see how the superconductivity varies from contact pair to do this as systematically as we can, given the constraints of the moiré world. And without belaboring the point, you can look as a function of increasing angle. And what you find is that at low angles, the electron side has a larger patch of superconductivity, a higher TC as a function of these tuning parameters. Eventually, it weakens and even disappears at the highest twist angles. The holes have the maximum TC at a higher twist angle and persist also. Superconductivity persists to higher twist angles. So we can compare what was the strength of the sawtooth with the strength of, that is the TC of superconductivity that we get out. And surprisingly enough, they have similar scaling. So I don't want to say anything more than that. This is a correlation between a transport property and thermodynamic property. There's no correlation with the gap itself, with the thermodynamic gap at nu equals plus or minus 2. That is, you see superconductivity in regions where we didn't see any correlated insulator. So at least we can say those are decoupled. We can't say whether this is the same underlying physics causing both superconductivity and the sawtooth and compressibility, but at least now we can say, hey, here's our same device. We measured it locally as best as we could with thermodynamic, with the SET, and then we took it out, measured it in the same device. The twist angles, by the way, didn't change as a result of all the fab that we did, and we can now compare it to the superconductivity as well. And so this is something still, I would say, in progress, still to be figured out. How much can you interpret from that measurement? But anyway, again, it's I think it's a nice example of combining global and local approaches. So let me end in particular by acknowledging all the people who did all of the work. Jesse Hoke was a graduate student who since graduated. He made this miracle super uniform helical trilayer graphene device. Yifan Li and Yuan Hu, graduate student postdoc, also have worked on all of these. And as I said, Aaron Sharp helped out with or did most of the transport measurements in this system. We got HBN crystals, which allow us to do all of this fun physics on these devices from the usual source. And I guess I didn't really talk about the physics that these guys collaborated on, but we had many theoretical discussions. And in particular, I want to highlight Tritep Devakul, who was the one who initially pointed out this relaxation effect in helical trilayer graphene. I remember actually the first day we saw a 2D spatial map that was showing this kind of super moiré modulation. I was sitting in the front seat of my car. The kid was in the back sleeping, and I was texting with people and said, "Hey, you gotta text or email Tritep to let him know." And he responded immediately, and we were all super excited because it was so cool. Anyway, and also Julian, who actually he's sitting here in the middle because he started off collaborating with these guys as his advisors, and now obviously is here. So let me end there. I'll just say, I think there's a lot of cool physics. I think maybe one of the most interesting things, again, if all of this topology is correct of the domains themselves, now you have something which is not just a trivial insulator or trivial system, not just a topological system. It's something where, as a function of spatial position, you have different topology. So you have this kind of mosaic of different topology. You can, in principle, control this network of topological edge modes. And so I think that's a really cool and unique aspect of their systems. We are, in the meantime, doing a lot of work to try and go beyond. So I showed some displacement field dependence. We can't put a metal top gate, or else it screens the SET, and we can't do our measurements. But we're hoping to put just a monolayer of graphene or a monolayer of a transition metal dichalcogenide, use that to control the displacement field and still be able to measure through it, which would be a lot of fun. And we're pushing this as collaboration with Ziek Shen and Cam Muller's group to push scanning probe microscopy down to Dilfridge temperatures. This guy has an electron temperature of 30 millikelvin. And again, my experience is if you cool things down, new interesting physics often appears. So very excited to push in that direction. Oh, and thanks for your attention.
Questions?
So Ben, I was puzzled when I hear those talks about not just Trilayer, but even layers.
Yeah.
Because I was told that having good vacuum is, I immediately make layers of water vapor stuff.
Yeah.
How come you guys can do all this magic stuff and you treat them, as far as I understand, as they're just graphene against graphene?
Yeah. So that's a good question. I guess I'm showing you the devices which worked. A lot of them come out imperfect and not ideal. We don't know why exactly. Certainly you want to avoid polymer residues. I think a real answer to your question is that actually the van der Waals adhesion is pretty good. So what you can do in many cases is as you're putting these things together, you can even sometimes squeeze out dirt, or you can use an AFM tip to clean dirt or to move bubbles around. I haven't shown you AFM images because oftentimes actually even for the pretty devices like this, they look disgusting. It turns out that a lot of the physics seems to survive. It doesn't always, and this is one of the Achilles heel. I mean, we waste so much graduate student and postdoc time making these devices, and finding a way to do it reliably, cleanly would be wonderful.
If nothing else, the yield is very low.
It depends on what you mean by very, but it depends who you ask. Pablo will tell you every device works, but that's because he doesn't hear about the ones that don't work, I think. I will tell you, we have, I don't know, 1 in 5, 1 in 10. These guys may tell you that actually I'm also lying and it's worse than that. I'm not sure I hear about all the failures, but it's at a level which it can work for doing science, but it's really not ideal. And I should say, as long as, so you can also have junk on top. As long as it's not conducting, we can measure through it, no problem. So we actually have HBN on top because that makes the most pristine interface that we can, but none of that would matter to us except if there's some Coulomb scattering from junk on top.
Other questions? Alfred?
There's one slide where you show the super moiré wavelengths can divert.
Yes.
Function some global strain.
Yeah.
Do you have any intuition about why? By just changing the global strain.
Yeah.
So little.
Yep. So let me go back to this picture here. So the picture that I would point two is I told you that locally you can have some relaxation where the atoms will move such that the states near the K2 point will, the atoms will move and you'll get those states living near the gamma point between K1 and K3. Really, this wavelength here is, so this is a super moiré wavelength, but it's an interference between two moiré patterns. So if you imagine a global strain that already does this for you, and you bring your K2 without needing any local relaxation, you bring it to what is effectively the gamma point. That is, you stretch the middle layer isotropically, then what you get is that actually this guy is already commensurate. So it's equivalent to one of these domains growing to infinity.
So I have a question about those samples that exhibit anomalous Hall effect.
Yeah.
What I always heard from David was they don't reproduce very well.
Yeah.
And what's your experience?
I would tend to agree with that. Okay, let me caveat this. So this is a measurement from Pablo Hirohiro's group, not our group. That is, have we seen anomalous Hall at all? I don't think so, right? So yeah, these guys are shaking their head. So we have not seen anomalous Hall in these helical trilayer graphene devices. This is a measurement from Pablo Hirohiro's group. They have a paper out which has many, many devices that they've characterized, and they see anomalous Hall physics in many of those devices. I don't know the statistics of how many they measured and weren't the right angle or didn't show, or those details I don't know. But there were several devices which qualitatively were not so different, I would say, from this. So I think it's not as bad as the HBN aligned magic angle bilayer graphene, where there is one device and only one device, as far as I'm aware. But it's tough. And this guy is even itself not quantized. I assume this is the best example that they put together.
You've answered the question, but
Yeah.
I just want to double check. So
Yeah.
I thought you had seen it, and you haven't. Stanford, there's not. In your
That's
view,
right.
you haven't seen it.
At Stanford, we have not seen anomalous Hall. We have not seen any intermediate features because the helical trilayer graphene device that I was talking about was at 1.5 degrees, where the bands, even though actually they're, if you integrate the compressibility, you get mu of n. So as you fill these central bands, actually mu only changes by like 25 millielectron volts, which is remarkably small, but is not one-to-one with the original non-interacting bandwidth. That is, we're measuring all the effects of electron-electron interactions. And that's true also for similar measurements in magic angle bilayer graphene. And my takeaway from this is, even though this is really small, that in and of itself is not enough to guarantee that you have strong interaction effects appearing in your device, and we see nothing there at intermediate filling. So we wouldn't expect for this device that the interactions are just not strong enough to see that. Yeah.
Anyone else? All right, let's thank Ben.